I'm Kevin Weil. I lead the analytics efforts at Twitter, and I'm here to talk about Hadoop and what we do with Pig to start understanding our data at Twitter. Feel free to interrupt me at any point. Let's keep it interactive, keep it fun. All right, so I'm going to talk a little bit about Hadoop, why, because no one has yet really talked about Hadoop here, why we need it, what you do with it, how it works. Then I'm going to talk about Pig and how that complements Hadoop and makes us able to analyze our data more quickly and more iteratively. I'll talk a little about the evolution of data processing at Twitter. Like everyone else, we started with MySQL, and talk a little bit how we've moved away from that. And then I'm going to go into what we use Pig for, and there are generally 3 steps to that in most analytics efforts. You generally start by counting things. And as you get more sophisticated, as you understand your counts, you start correlating things. And beyond that, you start doing some more of the sexy applications, research, data mining. So briefly, my background, studied math and physics, and then I studied more physics. Found myself in the middle of Silicon Valley doing a PhD while all my friends were starting companies and having a lot of fun at startups. So I dropped out, I joined a startup called Tropos Networks that did citywide wireless. So we covered cities with wireless networks in big cities like Philadelphia. The idea was that you'd be able to drive around in your car or be on a train and be on the same wireless network all over the city. And it was this interesting system of nodes that would mesh together. And there was a routing protocol. You'd be sitting under a tree, for example, on wireless. The packets from your computer would hop a few nodes through the mesh to a router that had backhaul. So there were interesting routing algorithms, and the nodes took a lot of statistics so that we could measure how we were doing and improve that. So that was kind of my first introduction to decent amounts of data. We had gigabytes of data every day. Still in the realm where we, I think, processed everything with scripts. Next, I went to CoolIris, which is a web media startup. Just out of curiosity, has anybody heard of CoolIris? All right, a few of you, cool. So we actually record a lot of data there about how users are interacting with the media that's showing up on the screen. And over the course of the growth at CoolIris, we had 5 million users or something, and so we were generating a lot of data. We got to the point where our MySQL queries were taking 10, 15, 20, 30 minutes. And our daily jobs were taking 16 hours. And so we switched to Hadoop and Pig. That was my first introduction to that. So there we were working with terabytes of data. About 6 months ago, I moved to Twitter to start the analytics team. And that's been an introduction to having a lot more data. So we use a lot of Hadoop and Pig for a whole bunch of things, which I'm going to talk about today. I feel bad, actually, with this. I really like this picture. And then I was working on my slides yesterday, and one of the guys behind me said, "Hey, that's what my cluster looks like." But I don't have to tell you guys. That's why we're here. Data's getting big. I saw from someone else's presentation, the New York Stock Exchange is generating a terabyte a day. That actually sounds low to me. I don't know about you guys. Every time you hear numbers from Facebook, they're growing. I was with some friends the other day, and they said 20 terabytes compressed today. I'm sure that's an underestimate. And then, as one of the speakers yesterday mentioned, you've got things like some of the big physics applications, CERN and the LHC, Large Hadron Collider, the particle collider that's coming online, is generating 40 terabytes a day, which is 15 petabytes a year. And that's after they throw out a whole bunch of data that they don't care about. I don't remember his statistic yesterday about something like 40 petabytes a second or something. That's their raw data, and then they throw everything out, and they keep still 15 petabytes a year of data that they need to analyze. And it's not only this. It's you have 10 terabytes now. You're going to have 100 terabytes next year. So whatever system you have, you've got to be able to plan for 10x growth or for 100x growth, which means even if something fits on a machine now, it may not next year. So you need to be able to shard your work across multiple machines. You can need horizontal scalability. Enter Hadoop. How many of you guys have worked with Hadoop in the past? How many are actually running it in some sort of production environment? Cool. So Hadoop is two things. It's a distributed file system because if you have a petabyte of data, it's difficult to store that anywhere. It's not going to fit on a single machine, so you need some sort of system for sharding that out and breaking it into chunks across computers. Hadoop does that, and it adds fault tolerance and replication to this. So when you store a big chunk of data on Hadoop, you have a file that's 10 gigs. It'll automatically break that apart into multiple pieces, move that to different elements to different nodes in the cluster, and then replicate that 3 times across the cluster to different racks, and to if it has some notion of topology, it'll try and spread the data kind of as widely as possible. With the idea being that I could go to your data center and set fire to one of your racks, and Hadoop would still be available. All your data would still be there. Moreover, Hadoop would notice that one of these racks was gone and that its data was no longer replicated 3 times and would start re-replicating the data elsewhere. So it handles that kind of fault tolerance, which is something you need when you're running clusters at scale. And that's also a bunch of code that you don't want to have to write yourself. The other part of Hadoop is MapReduce-based parallel computation, because if it's hard to store a petabyte, it's even harder to analyze a petabyte. MapReduce, which I'll go over in a second, it's a very generic framework. It's all key value based. Key value inputs, key value outputs at each stage, which makes it very generic. It makes it applicable to a lot of problems, but there are downsides to that, which I'll get to. One of the great things about Hadoop is that it's totally open source. So you can download it, you can modify it, you can watch it change and improve. It's managed by Yahoo. There's a lot of support for Yahoo for Hadoop at Yahoo. They use it for a whole bunch of their core infrastructure, so it's not going away. And there's a very vibrant community around it, which, as we all know, is one of the most important things for an open source project. Yahoo's probably the largest user of Hadoop. They maintain the largest, at least spoken of, cluster in the world, 4,000 nodes. They also, I heard recently in a talk, have it on 25,000 nodes across multiple clusters. And it's a powerful system. They sorted a terabyte of random integers, so 250 billion integers in 60 seconds on this 4,000 node cluster. It's a powerful system. And just a quick overview, in case people aren't familiar with how MapReduce works. So the example I'm going to use, we have, imagine we have, say, the Twitter table of tweets, which is big. You don't want to analyze this thing on a single machine. You don't want to do this in sequence. Imagine we wanted to count the number of tweets per user by just walking over this table. Say every row has a user ID. The way MapReduce works, as I said, it's all key value based. So your input is, your key is maybe some line number or something, and your value is the row in your database, essentially. Maybe it's a tab separated line with the fields. Your mapper function is where you split the data into chunks to be processed in parallel. And the whole idea here is that you don't have to group or sort or anything before you do this, because that would introduce a single point into your computation. You just split at arbitrary byte offsets in the file. You pass it off to, if you have n nodes, you pass it to n. You break it into n chunks and pass a chunk to each of your mappers. And the mapper will take that input key and value pair, and to count tweets, for example, it'll output the user ID as the key, and just 1 for the value. For this user ID, I saw 1 tweet. One of the most important phases in Hadoop, one of the things that I think people don't always understand, is the shuffle phase, which is where you end up sorting by the output key of your map. So in order to count the number of tweets per user, at some point we need to aggregate all of those. For a single user, we need to aggregate all of those in one place. So shuffle will sort by the user ID, and for each user ID gets sent to a single node. A single node may receive multiple user IDs, but it's guaranteed that, for example, all of my user IDs, my tweets were presumably split across all the mappers in that sequence. But when they get sorted by key, they may all go to the top reducer. And your tweets may all go to the bottom reducer. And someone else's tweets might also go to the top reducer. But the bottom line is that you can have more than one reducer. So again, you don't have a single point of contention anywhere in this system, but each reducer gets a chunk of data, but they get the contiguous chunk from a single user ID. And then your reducer is very simple. Given your input is the user ID and then a whole bunch of ones in this case, and all you do is sum them. And your output key value is the user ID and that sum, which is the tweet count. So with this parallel computation, we've calculated the number of tweets per user. If we had twice as many nodes, it would go just about twice as fast. There are some operational issues with sorting and shuffling the data around that may not make it exactly twice as fast, but it'd be basically twice as fast. And that's the power of Hadoop. So what's the problem? I don't know about you guys. I kind of want less Java in my life, not more. So with Hadoop, you're typically writing your analysis in Java. It's not always the case, but there are other options, but the standard is Java because that's what Hadoop is written in, and that's what plugs most natively into the framework. Also, I mentioned the flow is very generic. You have input key value pairs, output key value pairs at each stage, and you have this two-stage data flow. You have a map, and then you have a reduce, and then you get an output. It's pretty rigid. It's very generic, so you can map most problems to it, but at the same time, you have to map your problem to it, and that results in a lot of boilerplate code. It results in a lot of things that you want to do that should be simple because you do them over and over again. Results in a lot of code for that, which is error-prone. If you want to do things like joins, people have talked a lot about, it's NoSQL, you can't have joins anymore. That's not really true. They're just, you just have to have distributed joins now. And writing a distributed join in Java is not something that I ever want to do again. I'll show you an example in a second. It's tedious, and it's easy to get wrong. Also, most jobs you're going to do, most jobs with any complexity are going to have multiple stages. You're going to load some data over here, then you're going to load some other data, you might join them, then you might load some third set of data and put those together, filter by something. You're going to have a whole bunch of stages of your job, and when you're writing Java MapReduce, the way Hadoop exposes it to you, you have to manage that workflow. You have to understand your dependencies. You have to sort of wait for one job to finish, let it write data to disk, and then load that data back in, and make sure that your second job knows to load where the first one outputs data. So that it's just you end up having to manage a whole bunch of stuff every single time. Java's verbose enough. Writing MapReduce in Java, the way I typically do it, if I ever have to, is find the last one I wrote, copy it over, and then modify like 5 lines out of 200. So, and perhaps the biggest thing in day-to-day efforts and in the way we work in analytics at Twitter at least is a lot of times we don't know what we're trying to answer yet. We have a lot of data. We're still just starting to understand it. We don't know what the right questions are. And so it's of huge value to us if we can prototype quickly, if we can iterate. And having a compilation phase where you go back to Eclipse and then transfer some jar to your cluster is not quick. So here's Pig. And I want to. It's not the only solution to this problem. This is clearly an issue with Hadoop because there are 3 solutions that a lot of people use. There's Pig. There's cascading, which Chris Curtin will be up here to talk about next, and Facebook open sourced Hive, which is a SQL layer on top of MapReduce. I prefer Pig. For personal reasons, they're all great systems, and I'm going to tell you about how we use Pig. And I'm sure Chris is going to tell you some great things about cascading as well. So the bottom line with Pig, though, it's a high-level language. You can read it, and I'm going to show you this in a second. You don't have to think about key value pairs or map. You don't have to map the solution that you're trying to get into Hadoop's data model. You think about your data as sets of records, which is generally what data is, and you process it one step at a time. I've heard a lot of people say, and I think there's something to this, that it's easier than SQL, because when you start doing complex SQL, inner join with a bunch of data with a subquery, you end up with this like 7-line thing that's hard to parse and hard to understand. Pig is actually really nice because you do one transformation at a time. So you get to think one step ahead and only one step ahead, and you know, a sequence of steps you get to where you're trying to go. So really, one of the best things about Pig, I think I can show you a script here, and I think you guys can follow it. So good, it's readable. I'll give you guys a second to look at that. Anybody who didn't come in knowing Pig, want to take a guess at what this is doing? Yeah. If teenagers actually don't tweet. Kind of. No, so yeah, the first stage is we have some users comma-separated value file, which looks like it's composed of a username and an age. And the first thing I do to it is filter it, so looking for 18 to 25-year-olds, like you said. And then I load my pages file, which is maybe my weblog, right, or my Apache log. So username and the URL that they visited. And what I want to do is see, of these users, 18 to 25, what are the top 5 sites that they went to? So look, I get to join. And it's a single sentence. I just say join users by this and pages by that. Underneath, that turns into a complex, the same complex Hadoop job that I told you I never wanted to write. Pig will compile this into a MapReduce job. It can't do anything that you couldn't do in Java MapReduce. It just makes it easier. So once you've joined those, you group them by URL. And this is just a group by count star in SQL. And then you sort them. You order them by views in descending, so your top is first. And then you take the top 5. And like I said, you're going through one step at a time. Each line by itself is very, very clear, very readable. I think it actually leads to fewer errors in my experience. So just for fun, since I've been saying that Java MapReduce wasn't any fun. Yeah, really. You can come up on stage and check this out. It really is. This is from some of the Yahoo guys. So there's distributed joins here. There's multiple MapReduce steps going on here. I don't know about you guys. I kind of like that. So the real thing here is Pig makes it easier for everyone to do large-scale data analysis. A lot of companies have business analysts that know SQL. And these guys maybe know some scripting languages. They're not programmers. They do business analytics. And good luck convincing your company to switch to Hadoop if you say, I'm going to switch to this new system, and I need to hire 10 guys to try and understand it. So Pig is easily learnable by anybody who knows SQL. The Pig version there was 5% of the code. 5% of the time, I think that's generous in some ways. I think it would have taken me, it took 5 minutes to write that script, and I think it would have taken me a lot longer than 2 hours to write that Java thing and get it right. And you take a little bit of a hit for execution time in Pig just because it's a little bit more generic. It's doing things for you rather than you specifying every single knob yourself. But 50% is actually an upper bound in most cases. I usually see 20%, 30%. So what this turns into, if your job is 10 minutes, it takes you 5 minutes to write the script, 10 minutes to run it, as opposed to, maybe in Java it would have taken 7 minutes to run it, but it took you 2 hours to write it. One of the reasons we're all here is that we understand that innovation is driven by data analysis. There's an incredible amount to be gained by looking at this large data, but you generally don't know what you're looking at when you start looking at it. So being able to iterate quickly like this has huge value relative to iterating slowly like this. So a little bit about the way data processing has worked at Twitter. And I've only been there 6 months, so I didn't get the full backstory. But when I showed up, it was all SQL. It was one of the reasons I came to Twitter, was to start moving us away from MySQL and onto a Hadoop-based platform where we could analyze our data in a horizontally scalable manner. So, I mean, there's nothing wrong with MySQL. Everyone starts there. Most people should start there because it's the Swiss Army knife of systems. But it's not built for analysis, and you eventually will run into the bottlenecks. So if you wanted to do select count star from users at Twitter today, you could do it. It'll take a few minutes. You'll kind of wait for a while, but it'll get done. Select count star from tweets, I don't want to be around. I think I read somewhere that we passed 5 billion on the auto increment counter of our tweets. So that'll take you a while. Let alone trying to join these things and then group and then sort, which is essentially what we just did in that 5-line pig script. This is my nerd slide for people who run this stuff in production and are technical. I'll go over this quickly, but feel free to corner me afterwards. So we run Cloudera's free distribution, which I would recommend to anybody getting started or even anybody running it in production because they put a little more time, they test heavily, and they also will backport. You get the benefits of having some of the newer features because they will push some of the newer features of Hadoop into their distribution, and you get the benefit of all the work they do testing it. And it's free. You don't have to get a Cloudera support license or anything. We have modified Facebook Scribe, which is a log collection system, fairly heavily. So we collect all of our logs. We've written an Apache module that logs straight to Scribe, and we've also modified Scribe on the other end to stream to HDFS, to stream to the Hadoop file system, first of all, and to stream through an LZO compressor on the way in. So our data actually doesn't touch disk from the front-end machines all the way through until it hits the Hadoop file system. We need that because we generate a lot of logs. We're in the process we're working with Facebook to get that work committed back to Scribe. We've also heavily modified the Hadoop LZO code. So the people that have worked with Hadoop know that in general, when you gzip your data, it's a great way to save on storage space, but you lose the ability to split your file into chunks, because if you take a gzipped file and I hand you a chunk of it and I hand you a chunk of it, you generally can't just start decompressing in the middle of the file. LZO is block compressed, so if you're smart about the way you split, you can do that. The other reason that LZO ends up being perfect for MapReduce is that it sacrifices a little bit of storage space for being really, really fast. So LZO lets us save 4 or 5x on storage space. Compresses to about compression ratio of about 5x for logs, and we don't take a hit at all on the MapReduce side because it actually the CPU decompresses it faster than the disk can load it. And we've written custom input formats for Hadoop and pig load functions for all of these, which we're also in the process of open sourcing. So there's some Java MapReduce, there's some Hadoop streaming at Twitter, but getting back to the talk, the original purpose of the talk, most of the analysis and most of our interesting analysis is all done in pig. So I'm going to start talking about that. First of all, what data do we have? 3 real kinds of data. Semi-structured data, so we have lots of logs, and that's Apache logs, search logs, Ruby on Rails logs, which expose all sorts of data about timings and bandwidths and operational usage metrics. MySQL query logs, so that we can do the same thing with our database. We try and never actually touch the database. We always want to be cached, but query logs tell us how often we do hit the database. Logs for the rate limiter, and then per application logs for every application underlying Twitter. We have a bunch of structured data. So tweets, users, blocked notifications, which are spam signal, phones or devices that people have attached to Twitter to use SMS, favorites, saved searches, retweets, authentications, which are an indication of engagement. It's basically an audit line for every time a logged in user authenticates in any way to Twitter. SMS stuff, third-party clients, and then followings is kind of a normalized look at the social graph. It's followed, followee. And then finally, there's the social graph itself, which doesn't really lend itself to being map-reduced for a number of reasons. I know Emil's going to come up and give a good talk in a few minutes. So I said at the beginning, there are really three things that we're doing as an analytics team. And you kind of progress in phases from one to the next. The first thing is counting. You want to try and understand your metrics. And at first, you just want to know how big are they? How many requests do we serve in a day? What's the hourly variation? What's the geographic variation? How do external events influence that? And how has Twitter responded under load and strain from external events? You need to start counting these things and start understanding them so that you can compare to past experiences. What's the average latency? And what's the 95% latency? I.e., what's the latency such that 5% of users actually have a worse experience than this on the site? You want to watch that, and you hopefully want to watch that metric keep trending down. I heard a quote the other day that I really liked. What gets measured gets improved. Before you know these things, when no one's looking at these things, you don't know where you're failing and what you need to be working on. So take our requests and group by response code. What's the hourly distribution? Why does that vary? How does that vary across the different parts of Twitter, the API, even per application? Is there something with followings that's a little bit funky? How many searches happen a day at Twitter? Where do they come from? Are people searching from the home page? Are people searching from their profile page, search.twitter.com, from the API? How do their queries vary? Are people looking at different searches across the API than they are from the Twitter homepage? How do the homepage search, twitter.com, only is there for logged out users? So how do their queries look? People that presumably don't know Twitter as well, don't know what it's about. How do their queries differ from existing users that know about the service? How many unique queries and how many unique users? And how does that vary across geography or the type of search? Are people searching on both their profile page and on the API? How many people are using both? And again, geographic distribution. So I want to give a quick example of this as a pig script and also introduce some of the things that we take advantage of when we're looking at data in pig. So this is looking at where are users querying from. So are they coming from the API? Are they coming from the home page? Are they coming from the profile page, et cetera? Some things I want to show you guys. The very first thing, the $input files. So pig will do parameter substitution for you. Because generally you write a script, you're going to be looking over data from, say, I don't know, October 1st. What's the next thing you're going to want to do? Look at data from October 2nd. So there's native parameter substitution in pig so that you don't have to keep modifying your script. The next thing, what's this com.twitter thing? So you can write your own load functions in pig that load your data from your format and put it into a pig tuple. Because pig, like I was saying, you just think of data in tuples. And so it's pretty easy to plug in and write something that loads data in whatever format you have into any kind of initial tuple in pig. And you also get, some of those are char arrays, which is their string. Some of those are ints, and you can sort of natively parse things from text into ints, which is really nice because then you can do numerical operations on them. The next thing, so the first line in the script, we're loading. So that loader in particular will un-LZO, uncompress our data, and then apply a regex to each line of the resulting uncompressed data, grouping it into these fields. The next line, these are our search logs, so they have all sorts of stuff in them. They have favicons and they have trends, things we want to filter out, because in this case, we're looking at search queries. So we want to filter that. This is a native operation in pig. you're going to filter by, again, a custom function that we've written. One of the really great, wonderful, flexible things about Pig is that you can plug in your own user-defined functions. You can do that in SQL, but in Pig, they're first-class citizens. Pig is written in Java, so you write these things in Java. They're generally 10 lines. They're really short. And there's a lot of power in this. If this were easier in SQL, the world might be different. So in particular, this one takes one parameter, the request URL, and essentially just regex matches it against /search or something. You can actually do that natively in Pig. Pig has a native regex match operator, but we tend to encapsulate some of that logic in case it changes. So for the next thing, we again use another UDF. We have this extract search origin, which for reasons of history, you need the virtual host at Twitter and the request URL to figure out where the search came from. But again, we have flexibility. We have some strange custom logic that goes in there for historical reasons, and it's pretty easy to write a simple UDF that lets us extract that in Pig. So then at that point, our searches with type variable is just a list of origins. It's a list that says, homepage, 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 integrated search, API, API, integrated search, API. We group by that value, and there's this parallel keyword. That's Hadoop letting you control the amount of parallelism in the reduce phase. So if you remember the slide earlier, we looked at the map and the reduce. The map is always determined by the size of your input, so you don't generally control how many mappers you have. But Pig does let you control the parallelism, which is nice because if you know that you're doing some data-intensive job, you can up the parallelism. In this case, we're using parameter substitution again because maybe by default we want to have one reducer per machine or 4 reducers per machine in the cluster. Cluster size might grow. I don't want to have to go back and change all my Pig scripts. And then after you group, you count. And just that easily, we have searches by type. So we end up with origin, 1 million, API, 10 million, et cetera. And I guess I should emphasize, this is, 6 lines? This is a really easy script to write. And underneath the hood, this thing is getting parallelized across n machines. This can be a terabyte. This can be a petabyte. It'll just work. Pig abstracts away all of the kind of gory details from you, which is really nice. So after you count everything, the next thing you generally want to do in analytics is start correlating, looking at probabilities, looking at things that vary together, and looking at things that influence each other. So one of the questions we have asked, is how does usage differ for mobile users on Twitter? That's both, mobile users, you can say the guy with the iPhone who's using Tweety on his iPhone, and the guy in India who's using SMS via Twitter on an old cell phone. Do those people, do they tend to tweet more often? Do they tend to tweet less often? Again, we have large logs that Pig makes this really easy to go through and pull answers out. You might wonder if they tend to log in more, if they tend to log in less. You could argue that maybe people that are mobile are more consumption-oriented because they're out, they can check Twitter, but they don't have as much of an incentive to tweet. Maybe they don't come back to the site as much. These are things you need to understand. And we've done a lot of work on this. How about kind of the other end of things, people with third-party desktop clients, with the people with their virtual command center of like 9 columns in TweetDeck. Do those people tweet more? Do they go to the website still? Their usage pattern is entirely different because Twitter is presented to them in a completely different way. Cohort analyses, always fun. This is kind of fixing a variable. You look at all users who had some identical variable on a single day, say all users who signed up on the same day, or all users who tweeted on the same day. And then you watch them over time, and you see how they differ. What patterns emerged? Of users that joined in the same day, how many were still using Twitter 30 days later? And how does that change if you looked 6 months ago? of those users that stay, what made them stay? How did they become successful versus the people that didn't come back? What was their experience like? Doing cohort analysis has taught us so much about the way people use Twitter. And again, all in Hadoop all with Pig, because it's maybe doing a cohort analysis is a 30-line Pig script, but it's not a 500-line Java MapReduce. One interesting thing to look at when you're talking about correlating things is site problems. Twitter doesn't have these, but if they did, we'd be interested in what kinds of things go wrong at the same time. Even when you're not talking about an actual site outage, just when things spike, what correlates? What systems are not maybe properly separated in a big distributed environment? One of the worst things you run into is cascading failures. Something goes wrong in one system, which the other system doesn't expect, so something starts to go wrong in the second system, and then you have two systems malfunctioning, and so your third and fourth and fifth systems really start to go haywire. So understanding correlations in things like latency or simultaneous requests, memory load in systems has taught us a lot about the way our system works. From more of a product standpoint, you can look at what features get users hooked. When people join Twitter, what's their experience like? I think at first you're presented with a blank page that says, what are you doing? And you don't have any followers, you're not following anybody. So what can we do to improve that? And again, of the people that do get hooked, is it because they found some friends immediately, or because they followed Shaq, or they followed Lance Armstrong, or they followed Miley Cyrus? And if we can find those behaviors that led them to be successful, how can we encourage that with other users? Turning that question around, what features do successful users use often? It's a different question, because here you're talking about a group of users who understand Twitter, who have used it, who are very familiar with it, and have probably developed different usage patterns than the rest. So what do? Is it because are they successful because they're on a third-party client? Do they use both a third-party client and the website? Do they tend to retweet a lot? Do they have a lot of close friends? Is it that they follow celebrities? There's so much to explore here. And when it's as easy as a scripting language, we can do that relatively quickly. You have things like search corrections and search suggestions. These are things we don't do now that I would like to see us do, and that are pretty easy to do when you have MapReduce at your fingertips. Search corrections is things like, did you mean? And search suggestions is users who search for X also search for Y. There's some, I don't remember the number, maybe somebody has it in their heads, but some large percentage of Google searches are actually corrections or modifications. I know when I type something into Google and I misspell it, I just go forward with it because I know it's going to suggest the right thing to me. So that's a very valuable thing to have, and it just takes data analysis. And then finally, A/B testing. This is, again, something that we don't do enough of yet at Twitter, and we're moving in that direction, I think. Again, it's when you tweak a knob, what does that do to the other features of the site? What does that do to people's experiences? And if you expose that in a generic way on the site, then you can write pretty simple pig scripts which make that automatic. The whole thing with A/B testing is that if people have to work to get the results, they're not going to do it as much. But if you can make it into a framework that just every night, any A/B test that's going on the site gets turned into a page on the dashboard tomorrow morning, and people can go and see how one thing fared versus the other, you encourage this iterative, rapid prototyping environment, which makes the company better. So an example of correlating data. What's the relationship between people who have registered phones on Twitter, who have Twitter sign up or signed up to use Twitter over SMS, and actual tweeting? This is one of the things I alluded to earlier. So again, here's the first statement of this is register. So you can, just like you can load your own functions into Pig, it also comes with a jar called the piggy bank that has, 50 pre-implemented functions, a lot of math functions, things like that you can just use for free. So we're going to use correlation here. So again, we're loading two sets of data here. And note that we have two different load functions. These things are all over, and the fact that they're all over is a testament to how easy they are to write. We've written our own. Sometimes you even end up writing your own just to provide different views of the same data when you load it. So the first thing we're going to do here is we want to compute the correlation between whether or not the user has signed up or has a device registered, so 0 or 1, and then the number of tweets that they have. So the first thing we want to do is count the number of tweets per user. This is the thing that I alluded to at the beginning of the discussion about counting the number of tweets per user as a MapReduce step. And here it is in 3 lines of pig. So after we've done that, after we're sitting at tweets by user is calculated, then we want a co-group, which is essentially like an outer join. There are users that have registered devices that haven't tweeted, and there are users that have tweeted that haven't registered devices, and we want both of those in the set, so we don't want to do an inner join here. But pig has co-group as a native operation. At that point, we're generating the user ID. The way pig co-group works, this is more detailed than you need until you're actually writing scripts. But the way co-group works, you'll end up with a bag for each of the things that you are grouping by will turn into a bag of tuples. In particular, the devices will be a bag that's either size 0 or 1, depending on whether the user has registered a device, whether there was an entry for them in the devices table. And then tweets by user will be the same thing. There'll be a bag, or it'll be empty if they haven't tweeted. So again, we have the ternary operator as a native element in pig, so that the language is pretty free-form and expressive. And we're just generating the tweet count. At the end, this correlation function that we want wants each of its inputs to be a bag itself. So you need to do this group by all operation, which again isn't really important until you start writing pig scripts yourself. But we're just doing a little data gymnastics here. And then there's this function that we just call into, correlation. Compute the correlation of 2 gigantic data sets. And again, this is pig has the ability to make these eval functions, these things in yellow. You can make those sort of mini MapReduce jobs with a map phase, a combine phase, and a reduce phase themselves. So, because in general, you can't assume that these things you're correlating can fit in memory. In particular, one of these things might be the size of the number of tweets. So even these little evaluation functions can be MapReduce jobs in themselves. And at the end, we end up with a number, which is the correlation. All in, again, 12 lines of pig. So now onto the sexy stuff. Prediction, graph analysis, natural language processing. One of the most basic questions is, what can we tell about a user from their tweets? Because Twitter doesn't have a whole lot of data on our users. We don't ask for much when you sign up. We don't even ask for a sex or a geographic location or anything. We don't know your age. So what can we tell about you from your tweets? Are you popular? Do you have friends? Do you tend to follow people who don't follow you back? Similarly, what can we tell about you? What can we tell about you based on the people that you follow? Are you following celebrities? Are you following people that tweet at you? Do you have a lot of mutual followers? Is it a close kind of network? Similarly, with the tweets of the people that are following you. Presumably, there's some overlap between, there's some reason that each of the people that follow you. Maybe they like what you're talking about. Who are they? What are they interested in? And what can we tell about you from that? Finally, the ratio of followers to following often tells you interesting things on Twitter. Some of the people with a lot of followers get that way by following a lot of people. Some of the people with a lot of followers get that way because, for whatever reason, they inspire a lot of people to follow them. Maybe they're Tim O'Reilly and they're famous, or maybe they tweet really interesting content. Maybe they're funny. I don't remember how many followers Shit My Dad Says has right now on Twitter, but I can see most of you guys know the account. So one really interesting question is, what graph structures lead to successful networks? This is something a PhD student who's working with us has been focusing on a lot. So these kind of questions are, if I follow, Twitter's interesting. Its graph structure is interesting because it's not symmetric. I can follow you. You don't have to think I'm interesting. You don't have to follow me. So in particular, you can have a lot of one-way edges. But what's the impact of two-way edges? Do people who follow a lot of people who follow them back and have interesting conversations, judged by, say, the number of mutual @replies, does that make a successful user? Does that make a long-term user? What about if you get more complicated and look at threesomes, at triples? If A talks to B, who talks to C, who talks to A, you start to have these sort of tight social networks within Twitter, within part of the larger network. And how does that affect users and their relationship to the service? You can look at reputation, in the name of fighting abuse, things like that. If Tim O'Reilly follows you, you're probably not a spammer. Sentiment analysis. This is, as I'm sure you guys know, a difficult subject, but it's something that more and more companies are looking for on Twitter. I heard something the other day about movie theaters saying that you can predict the success of a movie very quickly from its first few days on Twitter, because people will A, tweet about how they feel about the movie, and then B, the people who haven't seen it yet will read those and will use it to influence their decisions. So you've got this kind of this decision, this loop here that either pushes your movie up farther or pushes it down lower, depending on how people start to talk about it. So sentiment analysis is very interesting to try and get right. It's also extra hard on Twitter because we don't have a whole lot of data to work with. 140 characters in a tweet is not a whole lot to derive meaning from. Another interesting thing that a lot of people, actually, throughout all of this, one of the interesting things about Twitter is that most of the things I'm talking about here, you guys can all analyze. Our data is very open. Our API exposes almost all of this. You might not be able to get the full corpus, but you can probably get a statistically significant sample and start doing it yourself. So people have looked into what features get a tweet retweeted. Is it more based on who you are or what you're talking about? Is it certain small sub-communities tend to retweet each other right and left? Or is it that you really did send around a really funny YouTube video? And when that kind of thing happens, how deep is the corresponding retweet tree? Do you have this string of A retweeted B, who retweeted that, who retweeted that, who retweeted that? Or do you end up with a broad thing? And how does that affect the way people react and respond to the tweet? If it's been retweeted by 7 people versus it's been, it's been retweeted by 7 people in a single string versus being retweeted by 10 people broad, one deep but 10 people. Long-term duplicate detection, we do a lot of streaming duplicate detection for things like abuse and trying to stop spammers who tend to send the same message out from multiple accounts. Long-term duplicate detection lets us understand trends on Twitter. It's very difficult to do. It requires a lot of resources, a lot of data, but our chief scientist actually has his PhD in duplicate detection, so we have an expert in-house. All kinds of interesting things we can do with machine learning. It gets a little bit back to what I was saying about not quite knowing the right questions to ask at first. How do we cluster users on Twitter? You could argue that there's maybe business users and personal users. Are those the right categories? Do they have more categories? Do those have subcategories? Do they overlap? My wife tweets about her letterpress business, and she tweets about venture capital from the same account. How do we cluster that? So there's a lot of machine learning, and this is stuff that we're still trying to do. We haven't solved this problem. And language detection. Language detection is really interesting because it tells you, about where people are coming from when they're using the service. It also, if you've used SMS on Twitter, you text something to 40404. You can tweet. You can follow people. You can actually sign up for the service that way. That's if you're in the US. If you're in Brazil, that's going to be an expensive tweet. So we try and get deals with the mobile carriers in the various countries, and one of the ways one of the ways we decide where to focus our efforts is based on the data, where people are tweeting from, because presumably wherever they're tweeting from is where there's an active need for a better mobile service there. And so much more. This is a small list. So one interesting application of research here, how do we detect bots and other non-human tweeters? As a company, we have no problem with this. There are lots of awesome automated Twitter accounts. I really like the guy that hooked up his cat with an RFID tag, and it tweets every time he goes in and out of the cat door. It's awesome. But at the same time, it's interesting from an analytics perspective. We want to both report on the total number of accounts and the total usage, and we want to probably give that same report based on humans, because bots tend to be a little more talkative, and it's just a different use of the service that we'd like to be able to factor out if we want to. So in Pig, this is, I guess it's both easy and hard here. The actual Pig script is pretty trivial, right? It's one of the easier ones I've shown you today. We load the data. We project it onto just 2 of the elements. We end up, so we group by user ID so that we accumulate all the tweets for a given user ID. Again, this is a common thing we keep doing. Wouldn't it be terrible if we had to write 100 lines of Java every time? And then we pass this into a UDF. And this is kind of cheating. I told you I was going to show you a Pig script about calculating bot probabilities. It's all hidden in a UDF. But kind of the wonderful thing about this is this was a function that our chief scientist had already written for other reasons, not related to Hadoop at all. It took a bag of data and does things like Jacquard similarity and stuff on the tweets to try and figure out how much they differ. But making this in Pig, we sat down and in like 4 lines of code wrote a wrapper that just called his function given some input Pig data. This function was written without any understanding that there would ever be something called Pig. And we were able to leverage this in 1 line of a script. So it's pretty powerful. So that's how we're using Twitter. To recap, I hardly need to tell you guys why Hadoop, but we all know how rapidly data is growing. You've got to have horizontally scalable computation. As soon as you have a whole bunch of nodes, you've got to have fault tolerance. You've got to have replication. But writing MapReduce jobs in Java is often harder than it should be. Pig makes Hadoop accessible. It makes it easy to write scripts. It also makes it easy for people who aren't system programmers to go and start writing MapReduce jobs. It chains together complex job flows. You don't have to think about the fact that some of these jobs that I have showed you up here generate 3 or 4 MapReduce steps that are combining data from different sources. When you have, I'm sure Chris Curtin will talk about this too, when you have complex job flows, you have dependencies that you need to analyze and order properly in Hadoop. Pig takes care of that for you. User-defined functions are first-class citizens. You saw that in every Pig script I used. There were these UDFs that were popping up all over because you tend to have custom logic when you start doing a lot of analysis. And one of the best things is there's this vibrant open source community. There's a team at Yahoo working on Pig daily. So you write your Pig scripts, and a month later they do a release, and your Pig scripts are automatically faster. It's a wonderful thing. The bottom line really is that at Twitter, Pig helps us understand our business faster, and that's the goal of the analytics team. Thank you. Any questions?
So what's the overhead of using Pig over your own MapReduce?
Yeah, I mentioned it in one of the slides. Oh, sorry. He asked what the overhead of using Pig for writing MapReduce as opposed to straight Java. It's getting better. It used to be something like it used to be something like a factor of 2.2 or something, and now it's a factor of they say at most 1.5, and I usually see 20, 30%. So again, it means your 10-minute job might take 12 or 13 minutes. I'll definitely take the more rapid iteration But it's a trade-off. We do have some jobs, either really simple jobs or jobs that need to be extra performant, that we do write in Java. Because if it's a 2-hour job, maybe you don't want to take the extra 40-minute hit. At that point, it becomes serious. So it's one thing a lot of companies do is write in Pig, rapidly iterate, decide what the right answer or what the right question is, and then when they understand that, you can then turn your Pig script into a Hadoop job in Java if you need the extra performance.
How do you deal with you said you do exploratory stuff. Do you have like a cluster for playing with Hadoop data and the real analytics cluster? How do you sort of internally handle that?
The question is, when we're iterating, how do we sort of separate that from the daily jobs that we need to have automated? That's the question, right? I guess the answer is we don't. There's a thing for Hadoop called the Fair Scheduler that has one of the guys from Berkeley, Matei, recently committed that lets you do a little bit smarter job scheduling in Hadoop. Natively, it's FIFO. So if I start some gigantic job that takes up all the resources for 9 hours, and you have a tiny job which would run in 30 seconds if allowed, you're going to wait for 9 hours for my job to finish. With this Fair Scheduler, you can allocate pools of resources to different users. And so for our nightly job, it runs as a different user. And we just set it up so that it can have 80% of the resources of the cluster. Other users get 20%. And then when the nightly job's not running, their 20% expands to the entire cluster.
How much luck have you had analysts who are more used to SPSS or R or SQL running their jobs in Peg or writing them?
A lot is the answer. That's why when I came to Twitter, it was a big kind of discussion. What framework are we going to use on top of Hadoop? It wasn't a question of if we were going to use a framework. It was which framework: Cascading, Hive, Pig. And the reason that we went with Pig is because I've had success teaching PMs who can write SQL, somewhat technical PMs, but PMs that aren't system programmers, PMs that just know SQL, how to write Pig scripts. And democratizing that kind of thing, getting more minds involved is definitely valuable.
Thank you very much. Round of applause.
Thank you.